So, what if you could actually interrogate a chemical? Ask it what it is and how much of it is hiding in a sample. Well, today we're diving into this incredible technique called voltammetry, and it does exactly that. It basically turns chemistry into a high-stakes detective story.
Think about this for a second. Imagine you're a forensic scientist, or maybe you're testing the safety of drinking water. You're not just looking for a needle in a haystack. You're looking for one single, specific molecule in a literal sea of trillions. I mean, how on earth could you possibly find it?
Well, it turns out you can just ask the chemicals directly. Scientists have figured out this amazing method that's, for all intents and purposes, an electrical interrogation. It's a way to put a chemical suspect right under the spotlight and get it to confess its identity and exactly how much of it there is.
All right, so every great detective has an origin story, right? To really get a handle on this powerful tool, we've got to go back to the beginning and meet the chemist who first figured out how to question molecules.
Our story kicks off way back in 1922 with a Czech chemist named Jaroslav Hajrovský. His invention, which he called polarography, was the granddaddy of modern voltammetry. It was so revolutionary, it gave scientists a brand new pair of eyes to see the chemical world, and it was such a big deal that it earned him the Nobel Prize in 1959. But that was just the start. Through the 60s and 70s, researchers took his ideas and just ran with them, making the methods way more sensitive and powerful, and really building the foundation for the amazing tools we have today. Okay, so how does this interrogation actually work? What are we really doing when we ask a chemical a question with electricity?
The official name for this whole process is voltammetry. And the core idea, it's actually pretty simple. You apply a controlled voltage, that's your question, to a sample. The chemical's reaction to that voltage creates a tiny electrical current, and by measuring that current, you get your answer.
Let's break that down. First, we apply a voltage. This is like the detective asking a very, very specific question. This question triggers a chemical reaction, where our substance either loses or gains electrons. That reaction is the chemical's answer. And finally, we measure the current that flows because of that reaction. That current? That's our clue. It's the piece of evidence that tells us both what the substance is and how much of it is there. And here's the most crucial part, the real secret sauce. The strength of that current, the size of that clue, is directly proportional to how much of the substance is in the solution. So a tiny little trickle of current means there's just a trace amount. A big rush of current, that means there's a lot. It's this beautifully simple, direct relationship that makes the technique so incredibly useful.
Of course, you can't just conduct an interrogation anywhere. You need a special room and a team of specialists to make sure it's all done by the book. In voltammetry, that room is the electrochemical cell, and the team is a trio of highly specialized electrodes. Yep, this whole interrogation takes place inside what's called an electrochemical cell. It's basically a small container that holds our chemical suspect, the sample we're testing, along with the team of 3 electrodes that are going to conduct the questioning. And here is our crack team of specialists. First up, you've got the working electrode. This is the interrogator. It's the one applying the voltage, and where all the action, the chemical reaction happens. Next, we have the reference electrode. Think of this one as the unbiased observer. It provides a super stable, constant voltage, so we have a reliable baseline to measure against, ensuring everything is fair. And finally, the counter electrode acts as the security guard, keeping everything in order by balancing the flow of electricity. Each one has a critical job to do to get a confession.
Now, a good detective doesn't ask every suspect the exact same questions in the exact same way. Nope, they adapt their approach. And voltammetry does the same thing. It has a whole toolkit of specialized techniques, each one designed for a different kind of chemical case.
Let's look at 2 of the big ones. First, there's cyclic voltammetry. You can think of this as a behavioral interview for a molecule. You scan the voltage up and then right back down again to see how the chemical responds, and that reveals all sorts of things about its fundamental properties. Then, on the other hand, you have pulse voltammetry. This technique is all about one thing: sensitivity. It uses these quick little electrical pulses to filter out all the background noise, which makes it absolutely fantastic for finding even the tiniest traces of a substance.
And if you really want to get high-tech, you have something called square wave voltammetry. This is the rapid-fire super advanced version. It's incredibly fast and sophisticated, applying pulses in a special square wave pattern to get crystal clear results in a fraction of the time. This is the tool you bring in for the toughest cases that need answers like yesterday. So we have this amazing set of tools, but what do we actually do with it? Why does all this matter in the real world? Well, its impact is literally all around us, from making sure our water is safe to drink to guaranteeing the purity of life-saving medicines.
The applications are just huge. And a lot of the time, voltammetry is the best tool for the job because it's fast, it's pretty inexpensive, and it is unbelievably sensitive. Our chemical detective might be on an environmental case, hunting for traces of toxic heavy metals in our water supply. Or it could be in a pharma lab, making sure the dose of an active ingredient in a new medicine is absolutely perfect. In forensics, it's finding tiny bits of evidence at a crime scene. And in research, it's the key to developing the future. Things like advanced biosensors that might one day diagnose diseases from a single drop of blood.
So just how sensitive are we talking about here? Get this. Some of these advanced techniques can reliably detect concentrations as low as 1 part per billion.
Let that sink in for a moment. 1 part per billion. That is an almost impossibly small number to wrap your head around. It's the equivalent of finding one single specific second in a time span of almost 32 years. That is the kind of needle in a haystack the voltammetry can find. No problem.
And really, that's the power of this whole thing. It gives us a language to communicate with the molecular world, a way to ask very specific questions and get direct, quantifiable answers back. It makes the invisible visible. And it kind of leaves you wondering, if we can already do this, what other hidden secrets are out there, just waiting for us to ask the right question?